Afternoon, nerds. Yeah, a couple people. Yeah, it's good. All right, so a couple people said it. Piecewise functions is the last topic that we're going to discuss in this chapter. We're going to finish this lesson today. We're going to spend Monday, Tuesday, and Wednesday reviewing for that chapter test that will be Thursday of next week. On Monday, my plan is whiteboard day, where we review the concepts that went catastrophically bad on the last test. So there's a few things that a lot of people missed, and those are the things that I want to focus on in the whole group review. I am in the process of creating the second test review to go with the test. I want to give them both to you on Tuesday. That way you have 2 days in class and at home after we've remediated the concepts that were really bad for everybody to try to get as much help and as much practice as possible, because I really, really, really want everybody to do better than they did on the last one. Okay? That's what I want. Anyway, piecewise functions, the very last thing. When I was an Algebra 1 teacher, 8 years ago? Yes, 8 years ago here. My first year here, I had a section of Algebra 1 AB. That's a double block class. It's 2 periods in a row. Period A, period B. You see those kids 2 periods in a row, 5 days a week. That's 10 sections of math a week. I taught them piecewise functions for 10 periods in a row. Monday through Friday, double blocked. And Friday, by the end of the lesson, I was just like, screw it, I'm done. I can't do it. I can't do it. We're moving on. If you got it, you got it. If you didn't, I can't help you anymore. Because it was remarkably frustrating to me because I couldn't figure out why they weren't getting it. And I was doing practice. I was whiteboarding. I had things around the room, like scavenger hunt type things. I was really trying, and they weren't getting it. And then earlier this year, Ms. Hamill says to me, the pre-calc kids, because she teaches AP Calculus now, she says the pre-calc kids, and she means the ones that she got on our campus, it's her first year on campus, she says, they don't like piecewise functions. And I said, I know. And she said, why? And I said, I don't know. I think it's a domain thing. And looking at the last test results, I think that we have a fundamental lack of understanding what domain means for a graph. This is a piecewise function. It is literally built out of pieces of other functions. And the pieces all have their own domains. Okay, instead of using the terminology domain for a moment, let's pretend it's you and your 2 siblings, older sister Susie and little brother Bobby. Okay, so I did that, sister Susie, brother Bobby. Okay, and we all know that in a household with several children, all the children are treated differently from one another. Everybody knows that the baby gets away with murder because they're the baby. Everybody knows that the oldest kid is held to the highest standards. You're supposed to be the example. And everybody knows that nobody knows who that middle child is. They're just forgotten about, okay? What you're looking at here is the 3 children. And I don't know if you guys caught it, but I said older sister Susie and younger brother Bobby. That means you're the middle child. Anyway, if these are the rules that each child is abiding by in this household, okay? This kid really wants to be a straight line with a negative slope. And we all know that straight lines go forever in both directions. And the parents go, that's great, honey. You want to be a straight line that goes forever, but you're not allowed to. You're only allowed to exist to the left of the number -1. So yeah, we have a straight line with a slope of -2, but only until the number x equals -1. It exists to the left of that. Bless you. Earlier I had somebody say, well, how do I know which symbol means to the left of? And I said, well, this symbol means less than. Less than is left. Less left. See, they both start with an L. Okay. Numbers to the left of -1 are less than -1. Now here in the middle, I guess is you guys, the middle child, we have this lovely V-shaped graph that we talked about yesterday. And you want to be a V-shaped graph for the domain of all real numbers. You want to go forever, left and right. Oh, sorry, folks. You could be a V-shaped graph, but you can't go forever left and right. You can only exist between x equals -1 and x equals 4. That means this V-shaped graph has basically 2 endpoints. One of them is a closed endpoint. One of them is an open endpoint. But Mr. M, why can't they both be closed? Well, because if this was a closed dot and that was a closed dot, this would fail the vertical line test, and this would not be a function. So if something has two endpoints, one will be open and one will be closed. I was asked earlier today, how do I know which one is closed? Equal to. Equal to is closed. If it doesn't say equal to, it's open. So you see here, this graph exists to the left of x equals -1. It tries to get to x equals -1, but at x equals -1, there is an open dot. It doesn't actually exist there. It tried. It didn't get to. The V-shaped graph does exist at x equals -1, but dagnabbit does not exist at x equals 4. And that's because this parabola U-shaped graph starts at x equals 4 and then never stops, reminding you that the arrow means never stops. Mr. M, we haven't reviewed U-shaped graphs yet. I'm aware, and that's why I won't have you graph any of them yet. That's next chapter. So then why is it in this image? Just so you can see that we can make it out of anything we want. And also, boop, for the first part of the notes, just because you don't know how to graph a parabola doesn't mean that you don't know how to follow the order of operations. Because just like yesterday, even if you have no idea what a graph looks like, you could just plug in x's and get y's out, right? And plot the dots. But for a piecewise function, you need to know where you're going to plug those x's in. What domain does that x fit in tells you where you plug that x in. This says f of x equals. That means my y values come from, well, it depends on which x you're talking about. And that's how we get our y's. So this first one says, figure out what y is when x is -3. I'd like you to look at these three rules. Rule 1, Rule 2, Rule 3. Which one allows, as a class, which one allows -3? 1, 2, or 3? Thank you, 4 people. The whole class. Which one allows me to say x is -3? 1. Right there, because -3 is smaller than -1. It's to the left of -1. I'm allowed to figure out what my y... Sorry, I just got these lips. I'm allowed to figure out what my y value is when x is -3 using this and this equation only. So let's see what we get. Oh, and this is, I'm trying to figure out what color I want to write with. This is when x is -3. We're trying to figure out what y is. And it fits here because it is to the left of -1. It's smaller than -1. So we say -2 times, and then we got this -4, and we throw this -3 here, and we just multiply. -2 times -3 is 6, and 6 minus 4 is 2. That tells us that our graph should have the coordinate -3, 2 on it somewhere. I don't know if you caught this, but this piecewise function is exactly what's up here in this box. See? Now, will you always have the picture to confirm your answers? No. But that's what answer keys are for. It's already on Schoology, sorry. I was going to say Blackboard. Blackboard's special little cousin. Anyway, -3, 2 is right there. -3, 2, yes. And look where it is. It's on the straight line because that's the part that allows x's that are smaller than -1. Next one. Looking at x equals -1. Don't be tricked. Which one allows this x? 1, 2, or 3? Class? 2. Some of you spoke. A lot of you didn't. That's scary. But -1 has an equal to bar right there. So x equals -1 comes from the middle rule. I would like you to notice that this open dot occurs at x equals -1. And if I wanted to figure out where that open dot was, I would plug this -1 into this equation. But I would know it's open because it didn't have an equal to bar. If I want to know where the graph actually exists, what the y value is when x actually is -1, I have to follow the equal to bar and I have to plug it into the middle. So we're reviewing yesterday's concept. Negative, absolute, I'm going to put a number right there, plus 4. Now -1 minus 2 is -3. This gives me the opportunity to remind you that the things on the outside of the SC value bars are like jail cell visitors. They're not getting in those bars. Okay? You can't distribute this negative to this negative and make it positive. What you can say is the absolute value of -3 is +3. Oh, jokes. There's a negative sign still sitting in front of that +3. And -3 plus 4 is 1. So I had better be able to find the coordinate -1, 1 on that graph up above And there it is. And it's closed in because it was one of the endpoints. Bless you. I'd like to get a whole class response. Would be great. Class, which of these three, 1, 2, or 3, allows x equals 3? 2. X equals 3 falls between -1 and +4, so this is the rule that allows us to plug in x equals 3. Negative absolute. I got this -2. I'll put that 3 in there in just a moment. There it is. And 3 minus 2 happens to be 1. Negative absolute of 1 plus 4 is -1 plus 4. Or 3. Oh. We should be able to find 3, 3 on our graph up there. And better than that, it should be on the V-shaped part of the graph because we use the V-shaped rule. 3, 3. And there it is. So, Mr. M, are you telling me that I'm going to have to just grab random x's forever to graph these things? No, that's not what I'm telling you. But in a pinch, you could. And lastly, x equals 7. Class, 1, 2, or 3 allows x equals 7? 3. There it is. There was a lot of people, or at least one loud person. But yeah, 3 is greater than, 7 is greater than 4, so I can plug it in to right there. And what color have I not used yet to plug in? I haven't used red. I don't have my good pen today. This is like my wish.com red pen. I left my good one at home. So I got this poor substitute. Order of operations. 7 minus 5 is 2. So we have 2 squared, which is 4. I had better be able to find 7, 4 on the quadratic up there, the parabola that we haven't reviewed how to graph yet, but look, there it is, 7, 4. We did it. Yay. So in a pinch, yay, Luis Simos. In a pinch, you could grab x's, plug them in, and get the y's. But that is not at all what we're going to do. Do you have questions for me before I move on, though? Are you sure? Okay. I don't hear you make noises very often, so it was like red letter day. Wish.com red pin letter day. Okay. This graph has 2 pieces, 2 rules. What I want from you is I want you to at least understand what shapes you're going to be looking for. This is what we did yesterday, V-shaped graph. There's no number in front of it, but we could say that there's a +1 in front, yes? So if there's a +1 in front, would this thing point up or down, class? Up. We're expecting an upward-facing V-shaped graph. And this is a linear equation, straight line, Algebra 1. Its slope is positive. So it's an increasing function. We expect this roller coaster car to be climbing a track, okay? So V-shaped graph that points up, straight line with positive slope. Our 2 rules are separated at x equals 0. Left less. So to the left of x equals 0, I'm going to have this V-shaped graph that points up. And to the right of x equals 0, I'm going to have a straight line that goes up and to the right, positive sloped. So how do we graph these things? The strongest suggestion that I could make for graphing piecewise functions is find and plot your open and closed endpoints. Find those first. Just trust me on that. Well, for each rule. So for this first rule, I'm going to find I have one endpoint and it's open because there's no equal to bar. This one will be open while this one will be closed. I'll find this one's endpoint in a moment. For now, I need to figure out this one's open endpoint. So I need to plug in x equals 0, because that's where the domain changed, to the first equation. Now I know I'm not allowed, oh, I meant to turn that red, might be. I know I'm not allowed to actually plot this point, and that's why I'm going to write that it's open at that x value. I know that whatever y I get to go along with this x, it'll be 0, some number, and I'll put an open dot there. 0 plus 3 is 3. And the absolute value of 3 is, uh-oh, black pen's dying. What are we doing here? Okay. 3 minus 6 is negative 3. So I know I have an open dot at 0, comma, negative 3. That is right there. Now we said that this is an upward-facing V-shaped graph, correct? Well, after you've decided from yesterday which way it points, I told you identify its vertex. So we can't say that this whole graph has a vertex, this whole piecewise graph, but we'll say that this piece of it does. This piece has a vertex. And the vertex from yesterday is what makes the inside equal 0, comma, the number to the far right. Or you could think about it as transformations. Its vertex should have been 0, 0. This said shift left 3, shift down 6. What makes the inside equal 0, comma, the number to the far right. This will be the only open coordinate associated with that V-shaped graph. Every other time I plug in an x value, I just have a dot. So I have a dot at negative 3, comma, negative 6. Right there. I want my graphs to be perfect because this is on YouTube and I'm trying to get that ad money. Jokes, I'm not monetized. So I'm going to use a ruler. You don't need a ruler. Don't worry, on the test, this kind of thing is multiple choice. I just want my graphs to look good for the video. Now, we know that this is the right side of the absolute value graph, and we all know, I hope, that there is also a left side. Several ways we could figure out that left side. We could say the axis of symmetry was here, so any point that I found on the right just bounces over to the left. What I don't want anybody to think, though, is that an open dot on this side equals an open dot on this side. That's not how it works. There was a single open dot. Everything else is just part of the graph. But if you wanted to, you could say, see how this was a perfect, pretty coordinate, up 1, right 1, because the slope in front was positive 1. So if there's 1 to the right of the vertex right there, there has to be 1 to the left of the vertex right there as well. And then connect your dots. And again, I just want good pictures because notes like that. Earlier, I had somebody get a little concerned. How would I know that this graph is going to go through the x-axis at negative 9? I go, well, you don't. That's not what was important. What was important is that you knew why it was at this dot. Because it's the reflection of that dot over this axis of symmetry. Now, I'm not drawing axes of symmetry on here as part of the notes because I want you to, but I do want you to see that it's just this dot that's been bounced over and I connected, and it went forever. If you wanted to confirm that this point is true, you could plug in negative 9. Negative 9 plus 3 is negative 6. The absolute value of that is 6, and 6 minus 6 does happen to be 0. But I'm not going to try to give you a trick question and just change the x-intercept on you. Gotcha! I won't do that on my test. That's just mean. Are you all comfortable with this piece of our function? If not, say something before I do the other piece. Yes, ma'am, Jelena.
How do you do the other point next to the vertex?
This one? I saw that my graph went through this perfect grid point and said, since that is 1 to the right of the axis of symmetry, I know its reflection is 1 to the left of the axis of symmetry. Or we knew this point was here. I know it's open. I know that. But its reflection wouldn't be open because that's the only one that is open, right, at x equals 0. So we could have said that's 4 to the right, so there's one that's 4 to the left as well. Or you could use the fact that the front of this thing is going to have a positive 1 slope and a negative 1 slope. This side was positive 1, so this side had to be negative 1. Lots of different ways to get there. You could also just grab the x value that is 1 to the left, negative 4. And you could plug in x equals negative 4. And if you do that, you will get negative 5. Lots of ways you can make it happen. Okay now? Cool. Any others on that part? No. Yes, sir.
Sir, why did
Ilya.
you choose to make, why did you choose the 0 for the top function instead of the bottom?
Because this one, okay, so I'm going to use 0 for both functions. But this one I specifically said will not be a true point. It'll be an open point. Because I needed to know where my V-shaped graph came to an end. 0 actually only exists for this one. So for when I plugged it in here, I specifically said it's an open at this 0. But when I go to do it for the second part, it'll be closed. And because it's the closed one, it's going to get plugged into the second equation. Before I do the math on it, though, some of you are thinking, but why didn't I just graph this thing the way that I was taught to graph straight lines in Algebra 1? Plot the y-intercept and then use the slope from there. Well, I'll show you why. Because you can't guarantee that the y-intercept is always part of its restricted domain. That's why. That's why I said just go with the endpoint. Because just go with the endpoint will always work. Whereas the y-intercept, which would have been -4, you can see it's not on my picture. Okay. So I'm going to test my endpoint. I'm going to throw in x equals 0, and we're going to see what we get. And oh, half of 0 is 0, and well, 0 minus 5 is -5. So I have a closed dot at 0, -5. Which just so happens to be, coincidentally, is the y-intercept of that graph. But that's a coincidence. Your slope is up 1, right 2. Up 1, right 2. Right there. And then connect your dots, throw an arrow on the right side because it never stops. And there it is. If you have forgotten how to plug in or use slopes, you could just plug in an x that is to the right of x equals 0. Get your next dot and connect them. Okay? Completely up to you. Are you comfortable with this example that has a V-shaped graph and a straight line in it? Anything you'd like to ask me about it? Because this is the only day we're practicing it. It's not Algebra 1 AB where I could spend 10 class periods working on it. Ladies, would you like to talk to me about it? Are you sure?
Good.
Okay.
Wait, actually,
Yes, there it is. All right, yes, let me hear it.
okay, wait, so you're supposed to be both open and closed?
Yes, because that x value is always going to be the boundary. One of them has to be open while the other is closed. Otherwise, you would fail the vertical line test. So I just need you to identify which one is open and which one is closed, and then you test the endpoint. And then either put a closed dot at that endpoint or an open dot at that endpoint. Okay? Is that good? Good. See, we got to ask this. We got to know. Any other questions? No? Yes, sir.
So those two functions, they like cross at the.
Well, they don't cross.
They're there though.
They both have an endpoint at x equals 0, but one of them doesn't exist there because it's an open dot.
So that one has to have an open dot.
One of them has to have an open dot because if you ever have two dots vertical from one another, you failed the vertical line test and it's no longer a function. So only one of them can get the equal to bar. And it doesn't matter which one it was. It's just whatever the equation says. There's no rule like, oh, the second one always gets it. No, it's just like, I mean, there was nothing that said I could have made both of these the equals, and then this one would have had no equals. There's absolutely no rules about that. You just read the equations.
But on that graph we just did, could you have made the one to the right? Could you have made that point on the left an open circle or no?
If this one was open, then that one needs to be closed. Otherwise, I have an x value that doesn't exist for my graph, which has no reason why it wouldn't exist. It's not like it was breaking a rule of a fraction or something.
So either one of those could have been open as long as the other one was closed.
As long as one of them is closed, yes. But you have to do what the equation says. So the way this is graphed, this is the only way it could have been done unless I change where the equal to bar is. Okay? Let's do a slightly more difficult example. And the thing that should jump out at you as odd is that deal in the middle. That -4 should seem strange. Mr. M, there's no x's. I know. Remember what f of x means. Y equals. So this thing in the middle literally means y equals -4. Can someone describe the graph of y equals -4 to me with one word? Or if you wanted to use 2 words, you could. I've always had somebody who was able to do it. Megan?
Horizontal line.
It's a horizontal line. And since we already know that, I'm going to go ahead and graph that part right now because that part's easy. We have a horizontal line at y equals -4 from this x to this x. This one is closed. This one is open. But they have the same y value. At -3, -4, I have a closed dot. And at 4, -4, I have an open dot. And then we just connect those two things with a horizontal line. There. I feel like that was the most challenging part of this question because it's like, where's the equation? Ah, the equation's y equals -4. The other two, they're V-shaped graphs. They're yesterday's material. See, this is us practicing yesterday's material. This V-shaped graph, because it's got a negative on the front and negative people frown, will point down. But it will only exist to the left of, remember, left less, to the left of x equals -3. I want to track down its open endpoint. It's an open endpoint, but I need to track it down. It'll be vertical to this, either above it or below it, but it'll be open. What is that x value? -3? It's following the order of operations here. Cleaning up the inside because we're treating those bars like parentheses. -3 plus 6 is 3, I think. Yes. The absolute value of 3 is 3, so this literally just says -2 times 3, which is 6. I wrote 6 because I said 6. -2 times 3. Somebody was making noise, so I wanted to wait. -6 plus 8 is +2. I have an open dot at -3, 2 for that V-shaped graph. Ah. I said open and then colored it in. That's an open dot. See, I tried to make it wider. I'm so sorry. God, I'm bad at my job. All right, let's see. What do we got next? It's a V-shaped graph. It's a V-shaped graph. That means it has a vertex. Its vertex is at what makes the inside equal 0? -6. Common term to the far right. Or you could think of it as shifted left 6, shifted up 8. Either way, we have -6, 8 as the V-shaped graph's vertex. And that is way up here. Let's see, -6, 8. It is up here. And I'm going to connect my dots between my vertex and my obviously open coordinate, because I wouldn't screw that up. There we go. If you need to imagine the axis of symmetry, go for it. You see this open dot? How it's 1, 2, 3 to the right of that axis of symmetry? I can go 1, 2, 3 to the left. 1, 2, 3. And it's a closed dot because the only one that'll be open is at x equals -3. And I can draw the rest of my V-shaped graph. There we go. Are you comfortable with that entire process? If not, say something. Yes, sir.
Is the vertex closed or open?
So every time you're plotting a point for a graph, it's technically a closed point. The only thing that is going to be open is its end point. Everything else is, like everywhere this pin hit, that's a solid closed dot. I'm only making the closed dots fat and obvious so we could see them. Vertex, if you look on my answer key tonight, is not a dot. I just drew a V. I'm just doing that because it's for easy note taking. Okay. All right. Well, then let's get the other V-shaped graph. This one is a V-shaped graph with a positive number on the front. Oh, and positive people smile. It points up. It points up. We need to know where its endpoint is. And this one will be closed. Hey, look out. Throwing my pen. This one will be closed because I see an equal to bar. Let's test this endpoint at x equals 4. And we will have a closed dot there. 3 absolute. I'll put a 4 there in a second. Four minus 6 is -2. But the absolute value of that -2 is +2. So that gives me 3 times 2 minus 7. That's 6 minus 7. -1. I have a closed dot at 4 comma -1, which is way up here. I see 1's closed and 1 is open. Vertical of one another. I didn't leave myself much space here. But my vertex is found exact same way. You can either do it by saying what makes the inside equal 0, comma the number to the far right, or you can use transformations. This vertex is from 0, 0 has been shifted right 6, down 7. Either way, its vertex is at 6, comma -7. And I am going to connect those two dots. If you wanted to draw, a couple little dashes to see the axis of symmetry for that thing, you could. And you can see that this dot is 2 to the left of the axis. So there's another dot 2 to the right of the axis. Connect them and slap an arrow on that bad boy. Boom. And then I would just ask my students if they have questions before we get to this last skill, because I do need to try to get this last one in before the bell rings in less than 3 minutes. It's not that bad, is it? Okay. I'm going to be real with you. Getting the equation of a piecewise function, I feel like, is even easier than actually graphing them. It's not going anywhere, but I do need to get rocking and rolling on it. I see 3 pieces. Okay, pay attention to this symbol. You ready? Tall, skinny S. Don't pick your pin up. Tall, skinny, backwards S. Don't pick your pin up, and that's how you make those braces. Tall, skinny S, and then backwards, tall, skinny S. If you needed to know. Thought I was just teaching math today, huh? Nope. This graph. Upwards facing, absolute value graph. The number in front, positive or negative? Positive. Check this out. It's got a vertex, and I can see a pretty point right there. I can use my slope trick that says go up 1, go right 2, to know that there is a positive 1/2 in front of those bars. The vertex should have been at 0, 0. It's been shifted left 6, inside opposite, down 1. And the x's it exists for looks to me like they exist to the left of left less -3. Does this symbol get an equal to bar? No, because it's open. Next. Here I have a straight line. I see this point is an endpoint. I see this point is a pretty point. And I can count the slope. 1, 2, 3, up 3, over 1. 3 over 1 is my slope. And my y-intercept is visible. +2. And then you just list the domain. Includes x equals -3, equal to bar. Does not include x equals 1. Come on, nerds, I'm not quite there yet. Killing me. And the last one points down, so negative. And if it was me, I would just count the slope. Crap. It's down 2, left 1. That's 2 over 1. I'm going to finish it. Vertex, then shifted right 5, inside opposite, up 9, and to the right of x equals 1, including. There it is. My nerds left me. God.